Japan. A land of sushi, anime, and ninjas. Deep in the Japanese rainforest, 4 Japanese men led by Mr. Shea banded together to solve an impossible task, to find how much work it takes to form Mount Fuji. Each of them had a clear idea of what they were going to do. Using the Japanese resources around them, and after much time, effort, and arguing, they completed what they set out to do. Here is what they did to prepare for the daunting task ahead. First one to complete the warm-up problems wins a free Xbox. Find the work done when stretching a horizontal spring with spring constant 500 N/m from a length of 20 cm to a length of 25 cm. Through Roberto Hooke's law, we know F equals kx and work is the integral of force. Since we know k equals 500 and the bounds are 0.2 meters and 0.25 meters, we can integrate to find the work done. Solve this integral. We have to triple integrate here because there are 3 integral signs and 3 variables. They cannot be split up because they depend on each other, so do the work plus. Find the equation of a circular cone in cylindrical coordinates with radius 2 and height 1 above the x-plane and graph the cone. Using the equation of a cone with x's we can derive the cylindrical equation. Since radius is 2 times the height, we find a constant. The cone has to be right side up, so we change the sign and find z-intercept. After the men had stretched their brain muscles, they decided to imagine the mountain as a cone. Using their sophisticated measuring tools, they found that the radius was 62,000 feet, the height was 12,400 feet, and the density was 200 pounds per feet cubed. They ended up with this problem. When studying the formation of mountain ranges, geologists estimate the amount of work required to lift a mountain from sea level. Consider a mountain that is essentially in the shape of a right circular cone. Suppose that the weight density of the material in the vicinity of a point P is G, P, and the height is H, P. The 4 old men had already taken physics a long time ago when dinosaurs roamed the earth, so they remembered that work is mgh. They discovered that weight density is milligrams over V, so they set work equal to milligrams over V times H times V. V changes over time, so they decided to use a triple integral to triple their work and find the work needed to lift the cone. B. Mr. Shea told them to use cylindrical coordinates because he likes cones. To solve for the upper boundary of R, they used a proportion and found R in terms of Z. Now they were able to integrate using G of P equals 200 and H of P equals Z. After performing a magic dance, they found the work to be 3.1 times 10 to the 19th feet pounds. With their super OP knowledge of cylindrical coordinates, physics, and triple integrals, the 4 men were able to lift the mountain with their bare toes.